Hey, welcome everyone. I'm going to go down and heat my tea up for just a little bit. I'll be back at 2:15. Throw whatever questions you have up on the board. All right, hi everyone. Welcome to the early class. It's a cold, cold day here in my neck of the woods. Drinking a lot of tea, trying to keep warmer. So let me know what you want to look at today. There will be a quiz during the last 15 minutes of class. There will be no need for the equation editor on this one. It looks like, for the most part, everyone has figured that out. Do use it to its full functionality. So if you have an exponent, there's a little button on the first tab that's marked like that. Think, like if you want to do 3 to the x, you push 3, and then you push this little button, and then is that right? Yeah. So that'll write the 3, and it'll put that up there, and then push the x. That does exactly where you want it to go. And also on the fractions, we still have a couple people putting the fractions in the incorrect form. Let's use that fraction button. All the basic manipulations are on the very first tab that opens up automatically. Sometimes you have to reach down to the last one for the antiderivative or limit. I'm pretty sure everything we do in this class, however, should be on one of those 2 tabs. If you're struggling with that still, you can't get it to open, why don't you schedule a Collaborate Learn with me? There's some things that I can look at and tell, but it's sort of hard to communicate either via telephone or via email. So if I can, what I can do with Blackboard Collaborate is I can see exactly what your screen is showing, and then I can offer you any suggestions. Or if there is no fix, I can explain that there is no fix to someone, and then maybe we can work on a fix. But there's going to be a number of times on the next test, especially where I'm going to look for answers that are definite integrals or antiderivatives. So I'm going to want to use that form. Not necessarily do the antiderivative, but express it, much like the last page in the activity that was due for the day with the snowfall, right? We needed the antiderivative from 0 to 6 of the accumulation function dt. So those are the ones. Quiz today. Yes, indeed, Aaron, there is a quiz today, and today's quiz will cover, let me think about it. It was sort of a takeoff. It was takeoff on the last quiz. I asked you what a definite integral will give you in terms of a problem. So the definite, I'll write out words of a problem. I'll ask you what this definite integral represents, and you have to tell me what it is and what the units are. If you want to go back and maybe look at something, you know what, why don't I sort of open up that last activity. I don't have it right here, I don't think. So I can go back and give you some information as to what it could look like. And activity 20, that's the one that you just finished for today. It could look like part C on problem 1. It could look like part B or C or D, I guess, on problem 2. Okay. So it'll be either, I'll give you some integral from A to B of some function of I don't know, some variable, d, whatever variable that is, or I will give you, say, a function 1 over b minus a, integral of some function d of that, or maybe one of each even, and you write to me exactly what each of those represents in the context of the problems and include the units. So that's today's quiz, taken directly from the stuff we just got done doing. And was there something like that on today's? I don't think there was. Today's was just, oh, sure there was. Yeah, problem letter I on problem 3, that would be where I give you the definite integral and you tell me what it is. Okay. So yes, it'll open up that with 15 minutes to spare. I was guessing that today's class will probably go a little short since there's only 3 problems. How do you do question 2 and 4? Question 2 and 4. How do you, okay, 2 separate things. How do you do question 2 and then 4 on those on number 21? All right, let's take a look at question 2 first. So we want the area bounded by those 2 functions. And the first thing I notice is that first function is 6 over x, and 6 over x has only one discontinuity. 6 over x isn't continuous at x equal to 0. Now, if I were really good at algebra and remembered my graphing, 6 over x is a function that looks like that. It has an asymptote both at x equals 0 and y equals 0. And then 7 minus x, that's a linear equation with the slope of -1 and the y-intercept of 7. So that has to go something like that. And that's why some of the reasons I had you mess around with the graphing a little bit early in the semester was if you understand the graphing, then all this makes a whole lot more sense. So there's the graph, and these 2 are definitely going to intersect twice. So there's sort of that fingernail-shaped region, like they're almost a half-moon-shaped region. That's going to be the area that we're looking for. There's just two curves given. So let's see if we can figure out where these 2 points of intersection are. Those would be the ordered pair that solve them both. And in order to get that, we'll set those two equations equal to each other. I did one just like this on the practice video on the getting ready for this class. Let's clear out the fraction first off by multiplying both sides by x. 6 is 7x minus x squared, quadratic equation. I'm going to bring it all to this side to make it easier. Then I'm going to factor 2 factors of 6 that add up to a 7 would be minus 6 and minus 1. And then if I set those equal to 0 and solve, I get x is 1 and x is 6. And what I like to do with those is make sure that they both make sense and I get the same value in both. So I'm going to write the two functions up here. And here's my big double check, and this really gets me out of a lot of trouble if I've ever made any. So f of x was 6 over x, and g of x was 7 minus x. Okay. I'm going to calculate, first off, I'm going to calculate f of 1 and g of 1, and I should get the same point back. If I plug a 1 in here, it's a 6. If I plug a 1 in here, it's a 6. There's that ordered pair 1, 6 that solves both of those equations. Now I said that there's 2 points that they had in common. One of them is here where x is equal to 1. The other one should be where x is equal to 6. And let's see if that holds as well. So now I'm going to calculate f of 6 and also g of 6. If I plug 6 into this equation, I get 6 over 6, which is 1. If I plug 6 into this equation, I get 7 minus 6, which is 1. So here's the other ordered pair where both of these graphs hit. It's the ordered pair 6, 1. Now, I could have done all of this without the graph, right? The graph just gave me a little better idea as to what was going on. But I've not used that graph at all in order to find those ordered pairs or to verify that they're the same. Oops, I'm 1 to 6. Make sure you get that there. Okay. So no matter what you plug in 1, you get back 6. Either one you plug in 6, you get back 1. So there's 2 points of intersection. Now, if I'm going to set this area between the curve up, what I have to do is go from the bottom limit to the upper limit. And the limits are always, in this class, they're always our x limits. So we're going from 1 to 6. We're going from here to here, just like we did on the area under the curve. And now we take the upper function minus the lower function. Now with this graph here, I can tell the linear is above the other. But if it wasn't there, here's what I would do. I'm going to choose any number in between 1 and 6. Those are the only 2 points where those two functions are equal. So if I choose a point in between there, the one will be on top of the other. Let's choose an easy one to evaluate. Let's choose f of, how about 3 versus g of 3. If I plug a 3 in this one, I get 6 divided by 3, that's 2. If I plug a 3 in this one, I get 7 minus 3, which is 4. 4 is a bigger number than 2. So my g function, in between here and here, my g function, my linear function, is a bigger function than my f function. So I'll take my big function, 7 minus x, minus my small function, 6 over x, dx. And now it's just a matter of doing the steps. And I only caught, I think, one person on the quiz who did a definite integral without doing the antiderivative first. So if this stuff is all written out here, make sure you take the antiderivative. You don't just plug in 6 and plug in 1 and subtract the 2. If you do that, that's pretty well going to give you 0 points. This is a definite integral, and you must do both of those steps. So without finding an antiderivative, this isn't worth any points. Okay, so here we go. I guess the parentheses here really aren't important because what I'm subtracting only has one term. So if there were 2 terms back here, then I'd have to remember to distribute the minus sign. I don't in this case. Let's go straight to the antiderivative. 7, the antiderivative of 7 would be 7x. minus the antiderivative of x would be 1/2 x squared, right? Raise the power by 1, multiply by the reciprocal of the new power. And here's the one case where the power rule on x won't hold. We have x to the first in the denominator. That's our natural log function for the derivative. So minus 6 natural log absolute value of x. And I guess if I wanted to be precise on that one, I could plug in a plus c for the antiderivative. That's not what I'm asked to do, however. I'm asked to evaluate this from x equals 6 to x equal 1. So take your crap calculators, plug in the value, see what you get when x is equal to 6. Tell me what that number is. Grab out your calculators, figure out what you get when you get x equal to 1, and then we'll do the subtraction and come up with the final solution there. But it's always upper function minus lower function. And the way you find out is you choose a number in the interval and see which of those is bigger if you don't have an idea what the graph looks like. So what do we have when we plug in 6? What do we have when we plug in 1? All right, 13.26 and 6.5. And if you do that subtraction, looks like you should get about a 6.76. I did that subtraction right. I was smart enough once to bring my answer key with me. Yep. I had a 6.75, so we're right on there. So there might have been just a little bit of rounding someplace in here. So 6.749 is what I got on the answer key. 6.75 would be fine. I'm not sure if there's just a touch of rounding error someplace in this one, but anyway, that pretty well wraps that one up. So antiderivative, upper function minus lower function. Okay, problem 4, parts B, C, and D. Okay. Take a quick look at that one. The answer key open, and sometimes the answer key is a couple semesters old, and I want to make sure that questions haven't changed. Thought I looked at it, but I want to double sure. There it is. Okay. Oh, I had that in a Word file. Interesting. All right. I wonder why I didn't know that as a PDF. Problem 4. So we want parts B, C, D. All right. Part B, what does 1 square area under the curve represent? Oh, all right. The area, we find that out by plugging the numbers in and what they stand for. So if you were to look at one little square under the curve, it looks like it's $4 per hour in height, and it looks like it's 40 hours wide. So multiply those two together, $4 per hour, multiplied by 40 hours. Each of those would be $160 of earnings. Part C, how much money did the internist make during the first 3 weeks of class? So that would have been hours, 40 hours a week. That would have been hours 0 through 120. So it'd be the area under the curve from 0 to 120. It would be this value. So there would be the expression for how much that that internist made. So it's the area under the curve. I suppose if I want to draw the curve up here, show it what it would be graphically. Let's see, we got a little count that's sort of concave up there. So it'd be this area. There's the first 3 weeks. There's dollars per hour. And here's the number of hours worked, 0 to 120. So let's get the antiderivative of this and then plug the numbers in. So what is the antiderivative? Part A as well. Sure, we'll go back and get part A, Courtney. So we need the antiderivative. This is a t function. I'll write the first part up. I'll let you write out the second part. Antiderivative of 6 is 6t. I can tell there's going to be a plus there. Get that next number right. E to the 0.001t. Then I'm going to evaluate that from 120 back to 0. So if you recall, if we were to take the derivative of this e to a power, we bring the derivative of the power down. But since we're doing the antiderivative, we're going to do the opposite of that. We'll bring the reciprocal of the derivative down. So it'll be 8 times 1 over 0.001, tens, hundreds, thousands. That's 1,000. So it looks like this would be 6t plus 8,000 e to the 0.001t. Someone evaluate this what you get when you plug in 120. I'll do it when you plug in 0 because I think I can do this one pretty easily mentally. Plug in a 0 here, it's 0. Plug in a 0 there, it's 1. This is definitely 8,000 on the bottom side. What do you get when you plug 120 into our antiderivative? Yeah, it looks like Cam sort of focuses sometimes on me and sometimes on the board. So if I just leave it up there, it looks pretty clear right now, huh? Yep, so we got that. Oh, maybe I'll write a little larger too. Maybe that'll help some. Now it's better. Okay, maybe for a while I was a little short on streaming capability. I know my wife works online too, but it looks fine. Good, fine now. So what is the value we get when we plug in 120? Oh, okay. $9,739. And if we subtract the one from the other, and I did have the answer here, I might as well double check it. Yeah, it looks good. Do the one subtracted from the other, it looks like you get somewhere around $1,740. This is plus the decimal after that, so yeah. $1,740, that's the amount that internist made the first one. Okay, so we want to go back and get part A, find the initial pay rate. Well, the initial pay rate is how much money was made at the very start. And notice the pay rate, that's the scale over here. And that's also the function that we're given. So the initial means before any time has ever gone, what was the pay rate? And here's my pay rate function. P of t was 6 plus 8 e to the 0.001t. Calculate P of 0. The initial is what happens before any time has gone by. And if you plug in 0 here, you'll get 1, and 6 plus 8 is 14. So $14 an hour is the initial pay rate. Okay, so let's see, we have part A, we have part B, we have part C. What was the average pay rate? Oh, that's nice. Now that we have this, the 1740, if we divide that by what, we divide that by, how many hours did she work, 120? Divide that by 120 and you should get somewhere around $14.50 an hour. And of course, it should be a little higher than that initial pay rate, right? She's getting this raises built in. Salary is always increasing and it's concave up. So let's see how far through was I supposed to go. A, B, C, and D. Yep, that's it. So we're all the way through D. Do I have any questions on any of these parts so far? Or do we have questions on E, F, G, H, and I? Sure. Okay, so this is one of those word problems that once you catch on, they usually go pretty well, but sometimes it takes a while to catch on. What does the area of the shaded region represent? Well, all the area under the curve represents the amount of dollars that was earned. Now, the question is, where are we going to mark the start of that earning and where are we going to mark the end of the earning? So in this case, it starts at 240 and ends at 480. Area under that curve, 240 to 480. Okay, let's see. I'm going to count the weeks. The first week is between 0 and 40. The second week, 40 to 80. Third week, 80 to 120. Fourth week, 120 to 160. Fifth week, 160 to 200. Seventh week, so there's the first and the second and the third and the fourth and the fifth and the fifth. So this is the start of the sixth week. It's 5 weeks done beforehand. Let me count again. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4. Oh, hang on. Let's start the seventh week. Right, there were 6 weeks that had already gone by. 1, 2, 3, 4, 5, 6. Those 6 weeks are done. Started the seventh week. End of 7, end of 8, end of 9, end of 10, end of 11, end of 12. So it's the total money that this intern has made from week 7 through 12, I guess would be a nice way of saying it, huh? For the start of the 7th week through the end of the 12th week, or the end of the 6th week through the end of the 12th week, or I don't know, something like that. But those are definitely the weeks as they go by. Remember, the first week goes from 0 to 1. That was 0, at least at that first 40-hour mark. So sort of want to make sure we get our hours counted correctly there, our weeks counted correctly. What does the area under the curve represent? That's the total amount of money she made during the full 15-week summer internship program. So that would be my answer to letter F. And it's measured in dollars. Now we're asked to find that total 15-week internship. Okay, well, we already had the antiderivative. We already had the antiderivative found before. The total money that internist will make will be the total area under the curve for the full 15 weeks. So it'll be the antiderivative from 0, 15 times, I guess that's 600 hours of 6 plus 8 times e to the 0.01 t dt. Might not have enough zeros in there. Let me double check. Yeah, an extra 0. There we go. We already found the antiderivative a couple of screens ago. That's 6 plus 8,000 e to the 0.001 t. Let's evaluate that between t equals 600, which you finished your 600 hours, t equals 0 when that internship first started. I will do the bottom number again because I can and it's easy. It's 8,000. What do you get when you plug in 600 hours? Whoops. What do you get when you plug in 600 hours for t? $18,001. Yeah, I like it. So $18,177 if we round to the nearest dollar. So how much did that internship pay? It looks like it paid a little over $10,177 to the nearest dollar. That's the area under the curve from the beginning to the end. Find the average pay rate. Well, let's see, that was 600 hours. So I would take this many dollars divided by 600 hours. And then I would think it's probably, it's got to be more than 14. 14 was the minimal one, right? Like it maxed out at about 20. So I would think that that would be certainly in the range of 17 or so. Okay. 13 weeks, not 12. Oh, okay. Let me go back and look at the weeks again. So let's see. It's week 1, week 2, week 3, week 4, week 5, week 6. So that's week 7, 8, 9, 10, 11, and 12. Yeah, that's weeks. I was right before. That's week 12. Week 12 goes from 440 hours to 480 hours. That's the week 12. So there's 7 weeks in there. 1, 2, 3, 4, 5. There's 6 weeks in there. I'm sorry. 1, 2, 3, 4, 5, 6. 6 weeks in the shaded area. Unless my shaded area is different from yours. Again, I'm working on the answer here. Let me look one more time. Oh my goodness. You are correct. I had an answer key that was a little out of date. You are right. All right. So back to the previous one. Yes, it was it was through week 13. You are correct on that one. My fault. I'm not sure why I didn't say this is a PDF or why it didn't come up as a PDF. They typically did. Oh well, explain what the last one means. It's from 80 to 200 hours. I'm going to make changes between this class and the next one, make sure everything is lined up the way it should. Yep. Okay. So 80 to 200 hours is the last one. So 80, after 80 hours of work, that's that 2 weeks are done. So I guess this would be the amount made from weeks 3 to or through week 7. I'll double check that one more time. Through 280, yeah, okay, good. I just copied the wrong number down. Right. 200 was not lining up. So yeah, there's the last problem was 80 hours to 280 hours. After 80 hours, that means you've worked, what, 40 hours a week? You've worked 2 hours or 2 weeks. 280 hours, that means you've worked 7 hours. I'm sorry, 7 weeks. So weeks 3 through 7, that would be that last little part on E. So I'm going to need to adjust my answer key. I have had my associates start to grade some of the backlog on activities. It seems to be going fairly well so forth, with a number of phone calls back and forth between some of them and me, but I think they're starting to catch on. So that ends up all of that whole word problem, doesn't it? And the idea here is we have to understand what that area under the curve represents and what the average represents as well, and how we get the area under the curve using a definite integral. So I think this is like the 5th or 6th example of problems that pretty well have worked the same way. It might be worth going back and looking at those previous activities so you can see exactly how the units fit together, exactly what the area under the curve represents. Because once you get that down, really the next test is pretty easy. There'll be a few antiderivatives to do, but this is the main focus of it. Next question, please. $16.97, yeah, that was the average pay. Number 1, all right. On number 1, we have just 2 curves given. And again, it's helpful to understand what these curves are graphed as. The second one, g of x is equal to x. That's a straight line with a slope of 1 and a y-intercept of 0. That's easy enough. F of x is a cubic equation. Cubic equations generally have a shape like this, or sometimes they have a little bit of a hill and a valley appearance to them. I notice if I plug in 0 on f, I get 0 back. So my bet is it's going to look something like that. Okay. Now again, it's not critical that you know what the graphs look like, but if you do, if you have some recollection from previous algebra classes, it really offers a better glimpse as to how to do this problem. So regardless if you do or don't, if I'm only given 2 curves, then they have to, if I'm going to find an area between 2 curves, then they have to intersect in at least 2 places. If you have 2 curves that don't intersect, then the area between them is undefined. There's no set specific area. So if you, unless you consider all that area between them, then it'll be an infinite amount of area. But if you're going to have a finite amount of area, you better have at least 2 points where they cross. So let's see if we can find those 2 points. If we can find them, then the antiderivative work gets set up after that. And the way we find whether or not they intersect is set them equal to each other. So we'll start with x cubed. Here's my f function. X cubed minus 6x squared plus 9x. There's the first one. And g of x is simply x. Take a look at my stream. It still looks okay. All right, so we'll set those 2 equal to each other. X cubed minus 6x squared plus 9x equals x. Polynomial equation, those are usually best solved by setting them equal to 0, so I'll subtract an x from both sides. And then I'm going to try to factor that one, because really that's about my only hope on this one. Factor out an x, I'm left with copy guard. Yeah, I did. X squared minus 6x plus 8. All right, now I'm going to see if I can factor that one down. 2 factors of 8 that add up to a -6. Sure, x minus 2 and x minus 4. Remember, those last two numbers have to multiply together to give that, and they have to add together to give that. Now that I have it factored, I'm going to set each of those three factors individually equal to 0, x equals 0, x equal 2, x equal 4. So in this case, I have 2 points where these, or 3 points where these intersect. There's a point there, there's a point there, and there is a point there. Since they have 3 intersections, it's going to take 2 separate antiderivatives, 2 separate definite integrals to find the total area bound by those curves. I did one like this on the prep video as well, so when you tuned into that original piece of learning how to do this, the problem worked out similarly to this. So it's 2 different areas. Let's call them a sub 1 and a sub 2. Now again, if I want to make sure that these are, that I haven't screwed up any algebra, what I'll do is I'll plug in each of those numbers in each of the functions. If I plug in f of 0, this is 0. If I plug in g of 0, that's also 0. So those two came out the same. Okay, so that's that point right there, 0, 0. What about if I plug in 2? If I plug in 2, this one is a 2, and this one is 8, 4 minus 24 plus 18. Yep, that comes out to be 2 as well. And then I'm going to plug in 4 last. That one's simple, that's 4. Here I get 64 minus 96 plus 36. Sure enough, that's 4 as well. Okay, so now I'm going to readjust my graph because I didn't do a perfect job of graphing it. They cross at 0, 0, they cross at 2, 2, they cross at 4, 4. So I'm fairly sure the graph looks like that. Again, it's not critical that you have the graph, but I find that it's somewhat handy to have it. Okay, so we're going to have 2 separate areas. Call that one a sub 1, call that one a sub 2. All right, let's look at a sub 1 first. We're going to take the bigger function minus the smaller function. Again, I'm going to remember that at x equals 0, x equal to 2, and x equal to 4, that's where those cross. Okay, so here we go. There are my 2 functions. Now, if I don't have the graph, what I'm going to do is plug a number between 0 and 2, and I'm going to choose 1. F of 1 is 1 minus 6 plus 9. That's, that's 4, is that right? Yep. And if I plug in 1 here, g of 1 is equal to 1. So that's the bigger of the 2 functions in the interval from 0 to 1. And that's how I drew it here as well. The curvy function is bigger than the straight line function. So to get the first one, I set the antiderivative from my lower limit to my upper limit. Take the bigger function minus the smaller function dx. Now, before I do the definite integral here, I'll certainly combine those like terms. So I'm thinking instead it's going to be 0 to 2, x cubed minus 6x squared plus 8x dx. Let's do the antiderivative. 1/4 x to the 4th. Let's see, it's minus 6, keep the x raised to the power by 1, minus 2x cubed. Same thing with the 8x. Keep the x raised to the power by 1, reciprocal of the new power, plus 4x squared. And at this point, I'm going to step back and make sure that I did this right. I'm going to take the derivative of this. Sure enough, that's x cubed. Good. Derivative of this, 6x squared. Excellent. Derivative of this, 8x. Perfect. Now I'm satisfied that I did that right. We're going to evaluate this from x equal 2 to x equals 0. I'll do the easy one. When you plug in a 0 for each of those x's, you get 0 in return. What do you get What do you get when you plug in x equal to 2? Yep, indeed we did. You plug in 2 here, you get 4. 4 minus 0 is 4. So that first area that I have on the graph there, that has 4 square units in there. Now we have to do the second part. And I'm only going to work so far through the second part, and I'm going to let you finish it. On the second part, we're going to figure out again, which of these two functions is bigger. I have the graph, so I know. If you don't have the graph, let's choose any number in between 2 and 4, where those 2 points were equal. And the obvious number is to choose 3. G of 3 is 3. That's a no-brainer. If I plug 3 in here, it's 27 minus 54 plus 27. It looks like that one is 0. Okay, so it looks like, again, as I guessed, the straight line was bigger than the bottom one. Set up the integral. Smaller to larger. Bigger function minus smaller function. 3 is bigger than 0, so it'll be x minus, and now the parentheses are important, x minus x cubed minus 6x squared plus 9x dx. Do the subtraction next. X minus x cubed plus 6x squared minus 9x dx, if I'm careful to distribute the minus sign through the set of parentheses. And then let's combine those like terms. Antiderivative from 2 to 4, we end up with negative x cubed plus 6x squared minus 8x dx. Around, right? Here we're subtracting one way, here the other time we subtracted the other way around. So when you looked at the previous problem, when we found a1, that was a plus, that was a minus, that was a plus. Okay. I'm going to let it go at this one, take the antiderivative, plug in a 4, plug in a 2, and see if you can calculate the area for part 2. So the total area that you're going to write down for your answer is going to be whatever we got from A1, that was 4, plus the whatever area you get for A2. So it's going to be 4 plus this still unknown. Again, take the antiderivative first, and then plug in 4, plug in 2, and do the subtraction. So that wraps up problem number 1. Pretty much, I'm leaving a few details to you. If you get stuck on those details, there'll be a chance to chat about it Monday, I guess. Yeah. Oh, you got 4 for the second area as well, Courtney? So if that's the case, then the grand total area between those two is 8. If someone else got that 4, then I'm probably likely to believe it, but make sure that you can do that. So if someone wants to jump in and say, yeah, I got the same number for that, or someone wants to jump in and say, no, I got something else, that's fine. Just let me know. I have the answer key here. Why don't I look? Yeah, I got 4 for both of them. So that's problem 1. Next problem. Number 3 it is. So if you look at number 3, there's a lot going on in there. And again, this is one of the reasons why in the early start of the semester, I had to work through so much algebra, especially the graphing part, because students just struggle like crazy with this. Last several semesters, especially last fall, it was unknown how do you graph any of these. And I think the graph is really helpful here. So let's set up our limits of integration by considering what we have. First off, we have the function x equals 0. Well, I'll put it in green. Here's the line x equals 0. X never varies. There it is. So that's one of the bounding curves, I guess, and not all lines. The next one is y equals 125. Okay. 25, 50, 75, 100, 125. There's a bounding line as well. So far I have this green one, and I have that black line. And then the last one is the exponential function. If you plug in 0, you get 25. This is an exponential function. We should know that those are concave up and increasing. We did a lot of graphing of the exponential function early on in the semester back when we were looking at the algebra stuff. So those are the three curves. So what's bounded by those three? There's x equals 0, there's y equals 125, and here's this curve. And the reason this is going to be important is when we get into the last lesson before the final, there's what's known as producers and consumers surplus. And this is sort of the wedge-shaped area that you come up with. So it's an economics study. So that is the area we wish to find. Okay. Well, we know the lower limit on this is already, that's 0. The question is, where do we find this point right there? Well, that's at the intersection of two functions. I'm going to write those equations down. This one is 25e to the 0.018x. And the other one is right there. That's y or f of x or g of x or whatever it was. That was when that one was equal to 125. So we need the ordered pair right there. I know the y value, that's given. I need to figure out what that x value is. So how am I going to do it? How am I going to find the x value that's going to give me the upper limit on my definite integral? Oh, it's the last problem, isn't it? So I guess we've worked our way through every single problem, every single part once this one's finished. So how am I going to find this missing value? I'm going to find the point of intersection between those two. Set the equation equal to each other, solve for x, you betcha. So 125 is equal to 25e to the 0.018x. We have an unknown in the exponent of e, so there should be a couple of fairly common steps. We've been using them all semester. What's the first step? Divide by 25, sure. Divide both sides by 25. See, there's 5 quarters and 25. $1.25 equals 0.018x. All right, next step. We have the exponential part isolated. So we want to know what this power of e is that results in 5. And what function tells us the power of e? Natural log it is. So you can do this one of two ways. You can either understand how natural log works and you say, so the natural log of 5 is equal to 0.018x. Because this asks again, when you see this written out here, this says e to what power is 5? Okay. Or if you want to take the natural log of both sides, that works as well. And the right-hand side, those would cancel. So now we'll divide both sides by 0.018. And we'll calculate a value for x. If I'm not mistaken, it seems like it was 94 something. Grab out your calculator. I'm going to look for my answer key. No, it wasn't. I got 89.4. I'll wait for that to be verified. 89.4. Yeah, look, just for the sake of consistency, let's just go with 89.4. That way everyone has the same answer. We're going to, it's just going to be approximation on this one anyway. All right. So 0 to 89.4. Now we're going to take the bigger function minus the smaller function. And as I have these written out here, it's obvious which is the bigger. If you don't know, then plug in x equals 0. If you plug in x equals 0 here, you get 125. If you plug in x equals 0 there, you get 25. And 125 is bigger than 25. So the bigger function minus the smaller function, 125 minus 25e to the positive 0.018x dx. That will give you the area between those two curves. So let's do those two steps. Do remember to take the antiderivative. If you don't remember to do that, I'm going to be very severe in my grading. This is an important idea of calculus. It's not plugging the function, the big number, and the small number. It's take the antiderivative first. Let's see, 125, that's 125x. What do you get for the second part, remembering our exponential problem? So I did the easy part of the antiderivative. Someone tell me what that next one is, and round that, whatever coefficient you have, round that for me. 1389. Let's go with that. I don't have that 0.018x. Evaluate that from x equals 89.4 to x equals 0. That rings a bell. I don't know if I have that written on my answer key. Would someone like to make sure they agree with that coefficient? Oh, never mind. I have a calculator here. That's an easy calculation. Yep, 1389 it is. Okay, good. So someone plug in the 89.4. I'll plug in the 0 because I can and it's easy. If I plug in the 0, I get 0 minus 1398. So this is negative 1389. What does someone get when they plug in 89.4? That's beyond the abilities of my calculator. $42.31, okay? So if I take the upper minus the lower, 42.31 minus negative 13.89, it looks like I'd be adding them together, 10, 14, 12, 6, somewhere around 56, 20 or so, huh? So the area between those two would be that many square units. That's it. Done. Any last minute questions? I guess if we're going to round this consistently, we round the last one to the nearest whole, yeah, we'll be consistent on this one too then. You're welcome, Courtney. See you all. Some of you may be on Monday if you have some questions. Good luck on today's quiz. It should go fairly quickly if you understand how all the expressions, the definite integrals work as far as word problems are concerned. And it'll open up, gosh, in I guess 3 more minutes. I'm giving you 15 minutes to do it. You should be able to finish it. And as long as you understand what's going on, it's a 2 or 3 minute quiz at the longest. Any questions after that? Please let me know via email if you're still struggling with any aspect of this course. Let's set up a time to meet in the next couple of days. I'll have some time. My goal tomorrow is to catch up on as much of the grading as I possibly can, and then I'm going to start writing exam 4 over the weekend, so that's ready for you for next Thursday. All right, good luck. See you in a bit.